Hello, everyone. Welcome to another discussion on PhysioEx10, your acid-base balance. You were asked to do all 4 activities, and as usual, you should be able to answer the questions or understand the concepts listed on the slides written here in blue. In activity 1, we were looking at what hyperventilation does to acid-base balance. Let's remember that hyperventilation is an increased rate and depth of breathing. As we exhale more of our CO2 is being exhaled. As our PCO2, that means partial pressure of CO2 in our blood, drops because we are exhaling excessive CO2, our pH will go up. I'll remind you that CO2 is considered to be an acid when we're thinking about our bicarbonate buffer system and that equation, that reversible equation that we learned about in lecture. As we lose acid, our pH goes up. And we remind ourselves, what are the reasons why a person can have alkalosis? They can either have too little acid, which in this case is CO2, or too much base, which is bicarbonate. How can a person have acidosis? They can have too much acid, in this case it would be CO2, or too little base, which would be bicarbonate. Let's go over activity 1. In activity 1, we, again, as usual, we start out with a baseline read. And our baseline, I'm highlighting here in purple. And our pH is within our normal, roughly 7.40 range. Then we're going to start hyperventilating. And as our rate and depth of breathing goes up, we can see that we are exhaling a lot of CO2. So our CO2 values are going down. And as we lose our acid, our pH is going up. Then we click normal breathing. But if you noticed, our breathing did not really go back to normal right away. Instead, the ventilation rate and depth dropped. There was no ventilation. And it stayed that way until the CO2 levels started to come back up. So this was the low point. They started to come back up and they got eventually back up towards 40. And again, our pH is starting to drop because we were retaining our CO2. So our maximum pH, our alkalosis was starting to improve. Let's move on to activity 2. In activity 2, we basically repeated activity 1, but now we're going to help this situation by looking at rebreathing. When we rebreathe, we are breathing back in, excuse me, our exhaled CO2. So again, our baseline read is shown here in the light blue. We have roughly our starting pH of 7.38, normal PCO2 of 40. And as we rebreathe our CO2, notice that the CO2 levels are starting to go up as we are rebreathing more acid back in. Notice what happens to our pH. Our pH is starting to drop down to 7.27. So we're going into acidosis because of the person rebreathing their CO2. Now, how can we combine exercise or activity 1 and 2? Let's say someone is hyperventilating and they are going into respiratory alkalosis, which is what we saw in activity 1. One way we can help them is giving them a paper bag and have them rebreathe their lost CO2, which is what the little cartoon is showing you here on this slide. By allowing them to rebreathe their CO2, it will help reduce their blood pH back down toward a normal pH value for our blood, which is roughly, again, 7.35 to 7.45. Now let's move on to activity 3. In activity 3, we were seeing how the kidneys can compensate for respiratory disorders. I'll remind you, if it is a respiratory disorder, then we cannot have respiratory compensation. And for this activity, you should be practicing what you would say or write for renal compensation for respiratory acidosis and respiratory alkalosis down to the tubular level. I will be describing these compensatory mechanisms like I have in lecture. But you should definitely go back to lecture and feel free to draw the reactions I'm about to describe that are occurring in the proximal convoluted tubule and in the late distal convoluted tubule. So in activity 6, again, we take a baseline read. We have normal CO2 and normal pH. And here are our normal, quote unquote, values of hydrogen and bicarbonate in the urine. Now what happens? We're going to see that CO2 goes down. So in the second experiment, CO2 goes down. In the second experiment, this is going to be respiratory alkalosis. Now, what kind of renal compensation will we occur? What will we see? What will occur? I'll remind you that carbonic anhydrase is found in both the proximal and distal convoluted tubule. Carbonic anhydrase, like every other enzyme in your body, is exquisitely sensitive to pH changes. After all, in PhysioEx number 8, for lab unit 1, we experimented with changes in pH on enzymatic activity. Carbonic anhydrase is no different. When the pH goes up in alkalosis, carbonic anhydrase activity goes down. In the PCT and distal convoluted tubule, the following reaction occurs. Water plus CO2 well, we say CO2 is hydrated. That means it's bound to water, into carbonic acid. This reaction is facilitated by carbonic anhydrase. And then that carbonic acid dissociates into bicarbonate and hydrogen. And I'll remind you, these are reversible reactions. So with the elevated pH, carbonic anhydrase, its activity will be impaired. So I'm going to cross that out. And because that reaction is not performing as well, or is not being completed as well, there's reduced enzymatic activity, we will not secrete hydrogen into the filtrate. Notice that the amount of hydrogen secreted in the urine has gone down. If we're not secreting hydrogen, then we cannot reabsorb the bicarbonate. Notice the bicarbonate is ending up in the urine in greater amounts because we can't reabsorb it. So that explains how our pH is going to be helped by the kidneys when they excrete more bicarbonate, a loss of base. This will help lower the person's blood pH. In contrast, in pink, we have a person going into respiratory acidosis. And in respiratory acidosis, I'll have you know that, let me write that back, that a lower pH actually increases carbonic anhydrase activity. This would mean more carbonic acid synthesis, followed by dissociation into hydrogen and bicarbonate. As the PCT and late distal convoluted tubules secrete the hydrogen, there is a sodium bicarbonate transporter where the bicarbonate is coming in with the sodium. Or another way you can think of this is let me erase that and start over and stick with what we discussed in lecture. That's probably the best thing to do. Okay, so here's our proximal or distal convoluted tubule. We have a hydrogen, sodium antiporter. Stick with what we have in lecture from Guyton and Hall. And as hydrogen is secreted, that hydrogen is going to bind to the filtered bicarbonate, and that is going to create carbonic acid, H2CO3, which will dissociate into water and CO2. And that can be on the way to the toilet. But inside the cell, we had water and CO2 forming carbonic acid, which dissociated into bicarbonate. And this hydrogen that is being secreted out through the hydrogen sodium antiporter. So the bicarbonate that was filtered is being lost in the filtrate, but the bicarbonate that was made in the cell is going back into the blood. And this means no net gain nor loss. The PCT is merely reclaiming the filtered bicarbonate. But in the late distal convoluted tubule, this same reaction is occurring, and the hydrogen that is secreting does not bind to filtered bicarbonate because it's not there in great quantities. Why? The PCT already took care of it, of course. And instead, the hydrogen is going to bind to other buffers like ammonias and phosphates. And now the bicarbonate that is made inside the cell, shown here, would enter the bloodstream, and this would be a net gain of bicarbonate. This explains why the bicarbonate levels in the last row of our data go down in the urine. And because of the increased hydrogen secretion, the hydrogen in the urine goes up. We are getting rid of acid. As the acid is lost and bicarbonate is kept or increased, our pH is going to go back up toward normal. In our last experiment, we are looking at respiratory responses to metabolic acidosis and metabolic alkalosis. Please keep in mind that for metabolic issues, not only will the respiratory system compensate, but also the kidneys, which I just addressed on the last slide. So in this experiment, we had a metabolic rate start out at baseline. Here's our baseline read. Relatively normal levels of bicarbonate and hydrogen and CO2 in the blood and a normal blood pH. Then we're going to see metabolic rate going up. Metabolism is the net sum of all anabolic and catabolic reactions. So we're going to go from 50 to 60 to 80. So here's metabolic rate going up. And you can also see that ventilation rate is going up. If metabolic rate is going up, there is more acid production as a result of those metabolic reactions. excuse me, metabolic reactions. So notice the acid going up. The respiratory system is going to try and exhale that acid in the form of CO2. So as the hydrogen goes up, if hydrogen goes up, it's going to bind to the bicarbonate in our reaction, forming carbonic acid, and that will dissociate into CO2 and water. So if hydrogen ions go up, CO2 levels will also go up, and you can see that here. And as a result, we're going to see an increased ventilation rate and depth. Increased levels of CO2 in the blood is the number one reason why your respiratory rate and depth goes up, trying to get that CO2 out. So as your metabolic rate goes up, hydrogen ion production goes up, more CO2 is going up. Of course, CO2 is a byproduct of metabolism as well. We see our pH dropping, and the respiratory system is trying to compensate by blowing out that CO2. In the next set of experiments, we're going to see metabolic rate going down. And as metabolic rate goes down, we're not making as much hydrogen. We're not making as much CO2. We're not having as much acid, and that means our blood pH is going up. And as your blood pH goes up, your ventilation rate and depth is going down in an effort to trap CO2, trying to lower your blood pH back down toward a normal pH value. Thank you for joining me for our PhysioEx10 acid-base discussion.